Any questions?
I actually had a question for the Module 3 homework on question 8. I wasn't exactly sure how to approach that problem.
Question 8. I'm pulling it up right now. Okay, there are two naturally occurring isotopes of copper. That one?
Yes.
Okay. With percent abundances of blah, 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 blah. Two naturally occurring isotopes of chlorine with percent abundances of blah, blah, blah. I'm going to round to roughly 70% and 30% and 75% and 25%, all right? If copper 1 chloride was subjected to mass spectrometry and individual formula units were ionized and no fragmentation occurred, what would the mass spectrum look like qualitatively and then quantitatively? Okay, so use the x-axis for the mass to charge ratio and use the y-axis for the relative abundance. So I'm going to share my screen with you now that we know all that information. Actually, I'm going to write down some information here in just a moment. So let me get to the Zoom. And, oh, we've got someone in the waiting room. So I'm going to share my screen with you, and it is going to have my Elmo. And here's the problem. So we have two isotopes of copper. We have copper 63, and we have copper 65. This one weighs, for all practical purposes, 63.0 U, and this weighs 65.0 U. And I know that because this is the mass number, and the mass number is the number of neutrons and protons. Each one of those weighs 1, so 65 of them weighs 65.0. And when I say each one weighs 1, it's 1.00. Okay, for chlorine, we have chlorine 35 and chlorine 37. So at this point in time, you should be able to tell me the mass of chlorine 35 as 35.0 U and 37 as 37.0 U. So really, that's one of the reasons why the number is called the mass number, is because it is really close to the number, to the actual mass amount, or relative mass unit, I should say. It really is a whole number, which is the number of protons and neutrons. Okay, so now I'm going to change what I'm looking at so I can see the Zooms, what you guys are looking at. So this is what you guys are looking at. We have, oh, I need to go back. We're going to need this information. So 63 is 69.17%, and this is going to be 30.87%, and this is 75.78% and 24.22%. And we're supposed to come up with a mass spectrum, and they tell us that we get copper 1 chloride. Okay, so that's all the information they have, and they want us to do this, where you get a mass to charge ratio, and here you get the abundance, which is also the intensity. And actually, for the abundance, that's not quite intensity, but it's close. So I'll show you what the difference is in just a minute. Okay? So first thing we have to do is figure out what's the formula. The formula here is copper plus 1 and chloride minus 1. How do I know it's a minus 1 on chloride? Well, chlorine is right here in group 7A. The charges on the nonmetal anions are as follows. Group 8A 0, 7A negative 1, 6A negative 2, and then it just goes negative 3, negative 4. It's just like a number line. How do I know this is a copper plus 1 ion? Because the name says so. Okay, so that means that this compound, the formula looks like this. Now, when we take into account that there are two possible copper isotopes, this copper could be either one of those. So let's pretend it's copper 65. Now, for the chlorine, what are the possibilities? It's one of these two isotopes. So you could have copper 65 and chlorine 35 for a total mass of 100 U. And the reason it weighs 100 U is because we know a chlorine 35 weighs 35. We know a copper 65 weighs 65. So these two particular isotopes together would have a mass of 100, the sum of these two numbers. You could also have a copper 65 and a chlorine 37 with a mass of 102 U. This first element, this copper, could also be copper 67. Oh, 63, I started with 65. And this could be chlorine 35, which would be 98U. And 98.0, I should put point zeros here. And this could be a chlorine 37, which would be 100.0U. So are you with me so far, Jackie?
Yes.
Okay, so are there any other possibilities? And the answer is no, there aren't. So we know we're going to see three lines up here, one at 98, one at 100, and one at 102. And you might say, well, there's two of them at 100. Well, the mass spectrometer doesn't know that they're different. They're both 100s. So we're going to see a 98, a 100, and a 102. Now, qualitatively speaking, which one of these do we think is going to be the biggest? Well, right off the bat, since there's two of these, we think they're going to be the biggest, but that may or may not be right, okay? Which one is going to be the smallest? And the answer is, whichever two isotopes have the least likelihood of showing up, if you combine those two, that should be the smallest peak. So if we take a look at above, we've got 37 at 24% and 65 at 30%. So the addition of these two, 37 and 65, that should be the smallest. Why? Because their isotopes are not very abundant. They're rare. Now, if we take a look at the two that should be the most abundant, we've got a 63 at 69% and a 35 at 75%. So those two, for a combination of what? 63 and 35 is 98. So this one should probably be the largest, except for one thing. We have to sum these two together, okay? So here, we know that this 98 is going to be tall. We know that the 102 is going to be shorter. The question is the 100 going to be as tall as the 98, shorter than the 98, and it will be taller than the 102. So this 100 could be something like that, could be something like that, who knows? This is a qualitative assessment. Here, we kind of don't know, but we know it's got to be bigger than that. It's got to be bigger than the 102. Are you with me so far, Jackie?
Yes.
Okay, so that's the qualitative. Now, let's figure out the actual quantitative, and it's not that hard to do. So I'm going to build me a Tony square. I'm going to put copper 63 here and copper 65 here. This one is 69.17%, and this is 31.87 or 83%. There's a couple of numbers. One of those numbers is wrong, but we're going to use the numbers that we're given. So 30.87%. And then we've got chlorine 75.78% and 22.22%. So this is 63. Oops. This is chlorine 35 and chlorine 37. So this box right here is going to be a combination of copper 63 and 35, which weighs 98. This is going to be a combination of 35 and 65, which is 100, This is going to be 37 and 63, which is 100. And this is going to be the 102. Now, if we take a look at the probability of the 102, it's going to be 21.22 times 30.87 over 100. So if we do the math here, 30 times 20 is roughly 600. 600 divided by 100 is 6. So this should be about 6. And I get 6.551. So you do the same here. So I'm not gonna do any more numbers for you. I'm just gonna do it in my head. This is 70 times 75. So that's somewhere between 49 and 56. So halfway between there is, we'll call it 52. So this is gonna be 52%. This is gonna be 31 times 76 over 100. And roughly speaking, that's 30 times 75. 30 times 75 should be around 222.5. And this one is going to be, let's see, that's supposed to be 24. 24 times 70, so 25 times 70. So 25 times 70 is going to be roughly the same as this guy. Let me think about that for a second. 22 times 70. 20 times 70 is 140. 30 times 70 is 28. So yeah, this is going to be roughly 22%. So when you map these out, this 98 is going to be 52. This 100 is going to be the sum of these two, which is around 44. And this one is going to be about 6.551%. So that's how you do the quantitative. Now, these numbers here are no good, the 52 and the 44. You got to do those yourself. But I've given you a great deal of help on that one, okay?
Thank you.
All right. All right. Any other questions?
Yeah, quick question. Do you have a practice test at all for the exam coming up?
Nope, I don't.
Okay.
It's too much effort for me to make one exam, much less two. You got a follow-up?
No, that was my only question.
Your follow-up should be, so what's the best way to study for the exam?
Okay.
Do you have a follow-up?
Sure. What you asked.
What I ask. I'm going to make it.
Any recommendations for studying?
Yeah, if you can do the homework problems without looking at the book, you're probably pretty set.
Okay,
Now,
thank you.
what can you do more than just these homework problems, because they're not going to be on the exam? The answer is do homework problems from the back of the chapter. And that's why I made the recommendation at the outset of the course, the best way to study for the exams is to do as many problems as you can. Do the ones from the back of the book where they have answers in the back of the book so you feel satisfied that you did it right. Fair enough?
Sure, thank you.
Okay, that's the best way to study. All right, any other questions? I'm trying to get back to my Zoom screen here. So you should see my hand here, is that right? Everyone see my hand?
Yes.
Yes.
All right, so since you guys don't have any questions, I have some. So here's the first question. Name the elements in group 2A, fifth period. So here's our periodic table. So we have to know where 2A is. According to the periodic table, 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. So these taller columns are the A's. You with me? So if we want 2A, we're looking right here. Fifth period, this is period 1, 2, 3, 4, 5. So we're looking for this particular answer, strontium. Now it says name the element. The symbol is strontium, ST or SR. The name is strontium. Okay, oops, wrong place. Okay, second period 4A. Oh wait, that's the one I answered, isn't it? No, it isn't. 2A fifth period, 1, 2, 3, 4, 5. Second period, so here's the second period. So let me erase this. So second period 4A is going to be carbon. Okay, how about the next one? Shout it out if you want to. Oh, you probably don't know the name of that one, right? Arsenic. How about this one? The halogen in the fifth period. You should know the name of that.
Iodine.
Say that again. Fifth period.
Iodine.
Okay. Halogen in the fifth period. Iodine. Well, I say iodine because if you say iodine, then you have to say bromine and chlorine and fluorine. It doesn't make sense. But if you say iodine, then you say bromine, chlorine, and fluorine. You with me? I don't know why everyone says iodine, except for the rules of English say that if you have an E after the N, it's supposed to be like the letter.
Force of habit, but yes, that makes sense.
So I just say iodine because everything else is ene. All right, how about this next one, people? Alkaline earth metal in the third period. Magnesium. So alkaline earth is second group. How about the noble gas in the fourth?
Krypton?
Krypton is correct. And how about a metalloid in 6A? So metalloid in 6A, 3, 4, 5, 6. I'm thinking it's probably selenium. What do you think? And actually, I'm thinking it's tellurium. Tellurium. So basically, the elements I'm circling are the metalloids. And you notice that as I circle them, they are on a diagonal. Do you see that? Now, they pretty much stop at tellurium, but there's two more, this germanium and this antimony. So this, when I look at that, I realize, okay, so 6A, here's 6A, tellurium. And I should put the symbol down because I put the symbol down for the rest. How about the nonmetal in period 2? And the answer is there's more than one, isn't there? There's carbon.
5 of them.
There's nitrogen, yes. There's oxygen. There's fluorine. And look at the spelling of fluorine. And then there's neon. Okay, look at the spelling below fluorine. What does that say? I've crossed it out. Sound it out. What does it say? Fluorine, right? Which is wrong. It's fluorine. Okay. Next problem.
Funny, quick question, just on
Yeah.
the periodic table as far as the exam. You had mentioned that for the quiz, you would be providing, I haven't done it yet today, obviously, you would be providing basically a bare bones periodic table.
Yeah,
Is that
just
the
like we
same
had
for
on,
the-
just like the one you had on that quiz from Module 2.
Okay, so same for the exam, or do we need to have this all memorized completely?
Same for
on
the exam.
Great, thank you.
You bet. All right. Let's take a look at this one here. We've got, put the following in order of smallest to largest mass. Now, this looks like a whole lot of work, doesn't it? Because we all need to turn them into the same type of mass unit, either atomic mass units or grams. I'm going to suggest, since there's such large amounts, that we do grams. Okay? So let me show you how to think this one through without doing a whole lot of work. We know that 1 mole of iron, which is 6.022 times 10 to the 23 iron atoms, is 55.845 grams. Okay? Now, what if you have 3.79 times 10 to the 24th? I'm going to rewrite that as 37.9 times 10 to the 23rd. So you notice I take that 24th and I take one of the 10s and multiply it times that. So I really have that many atoms. And that's a lot more than 6, right? In fact, I'd say 6 goes into that 6 times. So I have roughly 6 times that mass. So what's 6 times 55? 330 grams. Now that's an ish. Now what about 19.92 moles of H2? Well, I know that 1 H2 is about 2 grams. So 19 moles of this, which I'm going to round to 20, becomes 40 grams. So can we tell right away, without doing a whole lot of work, but doing some work, that B is smaller than A? Are you with me here, folks? And I'm showing some work here, right? Now here, for 6.5 or 8.576 mole of carbon, I know that there's 12 grams per 1 mole. And in my head, 12 times 8 is 96, plus a half more, half of 12, puts it at about, what, 102 grams. So here, this is an ish, but without doing a whole lot of work, I know which one is smaller and which one is larger. Are you with me? So this is the kind of work you might show on something like this. What's 7 times 30? 210? So we'll add a little more because this is like half. So instead of 210, we'll add it and add half of that, 16. What's 210 plus 16? 226 grams. So far, it's easy to tell which is the smallest and which is the largest. How about this one? 9.2 moles times 23 grams per mole. So here, I don't want to do 9.2 times 23, but I can do 10 times 23 is 230, right? But then I'm going to subtract 20 from that because it's not 10. So not 230, we'll call it 210. And here, this is a place where I'm a little bit leery about my what do you call it? My ishing. And I might want to do those calculations. All right. So here, I'm going to finish these up real quick. This is the same as 40.7 times 10 to the 23 atoms, which is equal to about 6 will go into that about 7 times. So that's about 7 moles. So 7 moles times 27 grams per mole. 7 times 27 is 140 plus 49, 190-ish. And here we've got 9.2 times 75 grams per mole. So again, this is 750 grams, but I'm going to subtract 175 from that. So that puts it more like at 680 grams. And then 100 moles of electrons, I'm just going to say that's really small. So we've got 100 moles times 6.022 times 10 to the 23rd times 9.11 times 10 to the minus 28 grams per one. So if we do that in our head, you can see that this 10 to the minus 28 and this 10 to the 23 and this 10 to the 100 comes out to be something like 10 to the minus what? 24. So something like 6 times 10 to the minus 24 grams. So this is the smallest, without a doubt, even though there's 100 moles. And if you look at all these numbers, this is going to be the largest, without a doubt. And these three right here, you might want to actually calculate because they're pretty close to one another, and the ish might not do it. So smallest, second smallest, and so forth and so on. This is going to be the second largest right here. Any questions about this one? All right, next. Which one of these has the highest mass percent chlorine? Now, mass percent chlorine is calculated by getting the mass of chlorine divided by the mass of the compound. And then you multiply by 100%. Okay? Now, in each of these compounds, what's the mass of the chlorine going to be? It's going to be 3 times 35.45 grams. What's the mass of the compound in each one of these going to be? Well, it's going to be the first element, which we're going to call X, plus 3 times 35.45 grams, and you multiply this by 100%. Okay, so that's the mass percent for each one of these. Which one's going to have the highest mass percent? The one with the highest X or the one with the lowest X? Well, higher X means higher numerator or larger numerator. Larger numerator I said numerator, that's wrong. Larger X means larger denominator. Larger denominator means smaller number. So if we want a high mass percent, we've got to find the X that has the lowest value. So look at all 5 of these. Which X has the lowest value? And the answer is boron. Boron is like a 10.8. Aluminum is like 27. Phosphorus is like 31. Arsenic is 75. Gallium 73. So this one is going to give us the smallest value for X, which will give us the largest mass percent. So the answer is BCl3, because you need the smallest X or the largest mass percent. And so do you see, you don't really need to calculate each of the mass percents. You've given a very good, reasonable explanation. Moving along. You guys are going through a lot of examples here today. This is how you study for the test. And it's my hope that you've done some of this type of stuff before. That's why I'm going through it kind of fast. I will be posting this later today so that you can review it again and look at it again if it's going too fast. So name the following and describe as ionic or molecular. Here's how I tackle these. These are nonmetals. Therefore, it's molecular. So I'm going to use the molecular name, which is chlorine trifluoride. The first element is named like the element. You only use a prefix if there's more than one. The second element is named elamide. And then you add a prefix, always. Now, this one is nonmetals. So it's molecular. So before I write the name down, I want you to think about what the name should be. And then after I write it down, see if you got it correct.
Trichloride.
Okay, so if you got nitrogen trichloride, you nailed it. Okay? All right. Hang on a second here. I got to do something real quick. Ooh. All right. If you see someone that needs to get in, let me know. Now, this is a metal and non-metal. So it's ionic. How do we name this guy? Strontium. And how do you name this guy? Sulfate. And that's good enough. How about this guy? Metal, non-metal. For the ionic compounds, what might make things a little better is if you do something like this. How about this guy? Well, we know we've got a tin. We know we've got 2 sulfates. We know the sulfates are -2s. What does the charge on the tin have to be so that the formula is neutral? And the answer is +4. So how do we name this guy? Tin 4 sulfate. So why a Roman numeral here, but not a Roman numeral here? And the answer is you do not use Roman numerals if the ion is from group 1A, 2A, 3A, zinc or silver. You do not use a Roman numeral for 1A, 2A, 3A, silver, or zinc. So when do you use a Roman numeral? All other instances for cations. Okay, so what about this guy? Metal and non-metal. Ionic. We've got 3 potassiums, right? And we've got a phosphate. So this is called potassium phosphate. Notice no prefixes for the 3 potassiums. You don't need those. Here, metal, non-metal, ionic. So you're going to name this aluminum sulfide. You don't need to tell people there's 2 aluminums, and you don't need to tell people that there's 3 sulfurs. You don't need to, because when you look at this name, you're supposed to realize metal, non-metal, aluminum is in 3A, so it's a +3. Sulfur is in 6A, so it's a -2. Then you do the switch and simplify, so aluminum 2, sulfur 3, which is the formula that we're given. You don't need prefixes here. Now this one, what's the last one? Non-metals, right? So this is molecular. So you're going to say oxygen trifluoride. Oh, difluoride. There you go. All right. Write formulas for the following. So here, this is going to be an ionic compound. The best way to write the formula is to come up with the ions first. So this is chlorate. That's the one I memorize. So that means chlorite is ClO2 and hypochlorite is ClO-. So that's how I get to the hypo. I memorize the 8 and then I work my way towards it. So that's the formula of the anion. That's the formula of the cation. I want one of each. So there's the formula of sodium hypochlorite. How about boron triiodide? Well, that one's easy. When I see that prefix, I know this is supposed to be a molecular compound. Here, if I don't see a prefix, I know there's one. Boron triiodide. aluminum perchlorate. So I know I've got aluminum with a +3, and here's my chlorate. So perchlorate means one more oxygen. So how do we write the formula of this guy? I need 1 aluminum, and I need 3 perchlorates. Now, if I do that, it's wrong because that means 43 oxygens. So when I have a polyatomic ion like this perchlorate, and there's more than one, I need to put a parentheses around it. Ammonium sulfite. Now this one, I know ammonium is NH4 plus. And I know that sulfite, well, I know that sulfate is this. So that means that sulfite is this. The difference between the 8 and the 8 is always 1 oxygen. The 8 has 1 more than the 8. Charge is the same, number of other atoms is the same. So here, when I do the old switch on these two, I get NH4, 2, and then SO3, 1, and I don't use parentheses, there's only 1. Now I'm going to kind of back it up because we're supposed to say ionic or molecular on each of these. This one is ionic, this one's molecular, this one's ionic, this one's ionic. Basically, you can see by my work that the ones that have ions are ionic. Now this is an interesting one because that's definitely a metal, potassium. This is phosphate. So what is dihydrogen phosphate? Well, it means exactly what it says, 2 hydrogens plus a phosphate. Now, what is the charge of the dihydrogen phosphate compared to the regular phosphate? And the answer is it's greater by 2. Okay, so for each hydrogen, you add a +1 to the charge to get the overall charge. So if these are the 2 ions, how many do I need of each? If this is a +1 and this is a -1, 1 of each. Sulfur, ionic, and this one's going to be molecular. Disulfur, dichloride, that's easy. And this one's going to be molecular, phosphorus trifluoride. Okay, moving along. Here's a calculation problem. Azulene, a beautiful hydrocarbon, is 93.71% carbon and its molar mass is 128.16 grams per mole. What are the empirical and molecular formulas of azulene? So the first thing when we do this problem is we realize we don't have all the percentages. We only have the carbon percent. And we're not even told what the other element is. So we have to figure it out. And the answer is based right here in this name where it says hydrocarbon. So carbon refers to carbon, of course. What does hydro refer to? Not water. It refers to hydrogen. So this is 93.71% carbon, and it's going to be 6.29% hydrogen. So how did I get the 6.29%? And the answer is I subtracted 93.71 from 100 exactly. Okay, so these two numbers should equal 100. Now to get the empirical formula, I'm going to pretend that I have 97.31 grams of carbon, and I'm going to turn that into moles of carbon. And I'm going to pretend that I have 6.79 grams of hydrogen and turn that into moles of hydrogen. And I can see the rough idea here, right? 12 going to 93, about 8 times, but not quite. So let's do the work here. 93.71 divided by 12.01, and I get 7.8027 mole. So I'm carrying an extra significant figure along. It's not significant, I'm just carrying it along. And then we get 6.79 divided by 1.008. This should end up being around 6.7, right? So we get 6.736. This is extra mole. Okay, and the way I like to do this, the book does it a little bit differently, but I do it this way. C 7.8027, H 6.736, because these mole ratios are really the ratios of the subscripts. And then what I do is I divide by the smallest number. Because what that's going to get me is hydrogen 1 and carbon something else. And I get carbon 1.16. Okay, so now we're in a quandary because that's not a whole number. So what are you going to do? How are you going to fix this so that you get that to be a whole number? Well, we could double everything. If we double everything, we get carbon 2.32, hydrogen 2. Well, that's not going to work. What if we triple everything? Well, we get carbon 3.48, hydrogen 3. That doesn't seem right, but it seems like we're getting in the right area. What if we do 4, carbon 4, or hydrogen 4? Then we have to multiply this by 4, and we get 4.64. And we keep working that up until we get to a nice number that we like. Okay? So let's see what we can do here. 1.16 times 8. Clear. 1.16 times 6. So if I have hydrogen 6 and carbon 6, I get 6.96. So I think maybe that might be the answer. Okay? So that's the empirical formula, C7H6. Now, how do we get the molecular formula? I don't like the way this is when it's working out, to be honest with you. I think this number is wrong. I'm going to do a quick check on the internet. Mass percent carbon in azulene. This makes me wish I'd done this problem before we started it. No, they have 97.3. They have 97.31. Did I do this right? Let's see, 93.71 divided by 12.
Looks like maybe the 3 and 7 are switched. If they have 97.3, that's 93.7.
Oh, no, they have 93.71. I said it wrong.
Oh, okay.
Okay, so I'm thinking that this might be the formula or something close to it. Let me do all the iterations of 1.16. 1.16, 2.32, 3.48, 4.64, 5.80, 6.96, 8.12, 9.28, and then 10.14. This is the one that's closest to a whole number, so I've got to go with that one. All right, so we're going to call that the empirical formula. Now, if this works out right, we should be able to take the molar mass of this and divide it into the empirical formula to get the molecular formula. So 7 times 12 is equal to what? You guys can't do this in your head? 84. 6 times 1 is 6, so we get 90. Yeah, this one is, I don't think this is written correctly. I'll be honest with you. So here's the deal, folks. We're going to switch the script on this problem. Here's the script.
I think I found something wrong with your calculation.
Which problem? Which part?
Can you turn back the paper? The calculation, the mole of H, I think you write 6.79. But
That's
actually,
not really going to affect the answer that much.
yeah, I understand it too.
That, I mean, this number needs to be dramatically different.
When I calculated, let's see. I got
We're going to flip the script here, okay?
yeah, sure. It'll be much
So
more better.
here, azulene is C10H8. What is the mass percent carbon? Okay, so how do we do that? Well, percent is always part over whole times 100%. In this case, what is the part? The part is going to be 6 carbons. The whole, or excuse me, 10 carbons. The whole is going to be 10 carbons plus 8 hydrogens, and then times 100%. So we're going to do this kind of on an ish level. 10 times 12 is 120. 10 times 12 is 120. 8 times 1 is 8. So we have 120 divided by 128, and then times 100. And we get 93.75%. And what is the number we had? 93.71. So it is correct. I'm just wondering, see, what we should be getting, honestly, is C5H4 for the answer. Maybe I did this wrong. 7.8 divided by 6.7. I think this one's okay. Let's try that one again, though. Someone said that may be wrong. Ah.
It's 6.229.
This is the problem.
Yeah.
6.29. That's the problem. Okay, so we get 6.240. So 6.240, 6.240, and this will probably come out nicer. So 7.8027 divided by 6.24. And here we get C1.25H1, which becomes pretty apparent that we multiply by 4 and we get C5H4 is the empirical formula. So do you see why 4 works out? Basically, you're going to take this guy and we're going to multiply by something that will turn both of these into whole numbers. So if you had something like this, what would you multiply by?
Three.
Yep, and you get C4H3. Okay, so that's the way to think about that. Now, that's the empirical formula. Now, the molar mass is about 64 grams. So to get the molecular formula, you're going to take this 128 divided by this 64 to get a multiplier of 2. So C5H4 gets doubled and it becomes C10H8. And so that's the molecular formula. All right, so there we go. Let's do another one here. We're just plowing through all these problems. Okay. Chromium oxide is obtained by heating chromium 3 oxide with carbon. Calculate the mass percent chromium in the oxide. So I imagine they mean that. And then use this to calculate the quantity. I think this is supposed to say chromium. And I may have written the problem there. Chromium is obtained by heating chromium 3 oxide with carbon. Calculate the mass percent of chromium in the oxide. Then use this to calculate the quantity of chromium 3 oxide required to produce 850 kilograms of chromium metal. So we're going to assume that they're saying that chromium is obtained. So basically, if you look at chromium 3 oxide, it's made out of chromium plus 3 and oxygen minus 2, which means when you do the switch and simplify, you get Cr2O3. When you heat this with carbon, you get chromium, and the other thing you get is CO2. Okay, this is a very common way of taking something that's an oxide of some metal and turning it into the pure metal is you react it with carbon. You can do the same thing with iron oxide. React it with carbon and you get pure iron. Okay, so this is kind of what's happening in the chemical reaction. We're supposed to calculate the mass percent chromium in the oxide. So the mass percent chromium is going to be the mass of chromium over the mass of the oxide times 100%. So when I take a look at 1 chromium, it weighs 52.00 grams. So we're going to have 2 times 52.00 grams over 2 times 52.00 grams plus 3 times 16.00 grams, and all of this times 100%. So if you don't understand where each of these came from, you need to let me know. I'm going to go over very quickly again. There are 2 chromiums in chromium 3 oxide. So here's the mass of the 2 chromiums. The mass of the oxide is going to be 2 chromiums plus 3 oxygens. So when we do this work, we get 52 times 52 is 52 times 2 divided by, this is going to be 104 plus 48, which is 152. And so for overall here, I get 68.42%. So this is going to have 4 significant figures in the answer because of basically the 52.0 here and here. Now, what is the mass percent? Here we go. Use this to calculate the quantity of chromium 2 oxide required to produce 850 kilograms of chromium. So this is kind of a weird one, but we have to understand what this means. This means 68.42 pounds of chromium per 100 pounds of chromium 2 oxide. Chromium 3 oxide, excuse me. So this mass percent means that many over that many. Percentage always means over 100. It also means 68.42 grams of chromium over 100 grams of chromium 3 oxide. What I'm trying to point out to you here is that when you have these mass percents, they mean over 100, and the mass unit has to be the same. Now, do you think this is going to help us here? I think it will, because that's kilograms and that's grams. But I'm thinking to myself, if I can use any mass unit I want, can I use kilograms instead? This last one that I've written, does that still mean 68.42% if I use kilograms? And the answer is you bet your bippy. So if I want 850 grams of chromium, how much of the oxide do I need? Well, I'm going to put 100 kilograms of chromium 3 oxide on top and 68.42 kilograms of chromium on the bottom. Can I use this upside down? And the answer is absolutely. Why am I using it upside down? And the answer is this should be kilograms of chromium so that these cancel. Okay, so let's find out how much of the oxide we need. Okay, so my calculator says 1242.32 blah, 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 blah kilograms of chromium 2 oxide. Now here you'll notice I put the labels in so I can see that the right things cancel. How many significant figures should the answer have? And why? Have you got an answer?
2.
2, 6.
The answer is 2, because 850 has 2. So how do we write this with 2 zig figs? There you go. Any questions on that one? All right, here's a good one. This one's not a calculation one. The formula of barium molybdate is BaMnO4. What is the formula of sodium molybdate? So this is not a polyatomic ion I asked you to memorize. We have to figure out what's going on here. First of all, when we look at this barium, we know this is a metal. And we look at this molybdate, we have to assume that this is some sort of polyatomic ion, because we know the names of all the monoatomic ions, right? We know their names: carbide, fluoride, nitride, phosphide. This has to be a polyatomic ion. So given this as being the formula, what part of this formula is the barium? And the answer is this. So that's the barium part. What's the molybdate part? It's got to be everything else. Well, what's the charge on a molybdate? Well, I don't know. What's the charge on a barium? Well, for barium, it's right here. So what's the charge on a barium ion have to be? +2, because it's in group A. Now, if you have exactly one of these and exactly one of these, and together their charges must add up to 0. What's the charge on a molybdate have to be? Has to be -2. So that's the whole process for going through figuring out the charge on molybdate and its formula. Okay? The first part of the name is the cation. The second part's the anion. Clearly, the barium refers to the Ba, so that means molybdate must refer to everything else. And because this is a metal and presumably a non-metal, and it does have non-metals in it, the oxygen, presumably this is a polyatomic ion because we don't know that name. We've never seen it before. We know all the single ion anions, and we just went through some of them. So this has got to be the formula of molybdate. And the reason it's got a charge of -2 is because when you have one of each, and if the charge on barium is +2, then the charge on the molybdate must be -2. Okay, so now how about sodium molybdate? And the answer is, well, there's sodium. We just found out that molybdate is a -2. So we do the old switch. So we want 2 sodiums and we want 1 molybdate, and there's your answer. Any questions about that one, people? So we can figure out the formulas of these things. Even if we don't really know what that is, we can figure it out. Okay. I have lots more of these to do. Let's do this one here. Pepto-Bismol, which can provide relief for an upset stomach, contains 300 milligrams of bismuth subsalicylate per tablet. What amount of active ingredient is in the tablet? So this is the active ingredient. So we're going to do carbon, hydrogen, bismuth, oxygen. Carbon is 21, we're going to say moles, times 12.01 grams per mole. Hydrogen is going to be 15 moles times 1.008 grams per mole. Bismuth is going to be 3 moles times 209.0 grams per mole. And oxygen is going to be 12 moles times 16.00 grams per mole. So how many grams do we get out of each of these? Let's figure it out real quick. 21 times 12.01, I get 30. I get a wrong number. I get 252.21 grams. $15.12 grams. $627 grams. And 192.0 grams. This should be 627.0 grams. So 4 zig figs here, 4 zig figs here, 4 here, 4 here. So that means that when I add these all up, I'm going to round to the 10th. So I add these all up together and I get 186.3 grams. So to figure out the active material per tablet, I'm going to take my 300 milligrams, multiply by 1 gram per 1,000 milligrams, and then multiply by 1 mole per 1086.3 grams. And that should give me the amount. So when they say amount, they're referring to how many. And moles is a how many. Okay, so let's do the work. 300 divided by 1,000 and divided by 1086.3. And I'm going to put this in scientific notation because it's a very small number. We get 2.76 times 10 to the minus 4 mole. Any questions there? Go ahead and turn your mic on and ask away.
Yeah, is that a standard when you said amount would be referring to the moles?
Yeah, amount refers to how many, like how many donuts? A dozen,
Right,
that's an amount, right?
Okay,
So that's what amount refers to. If they wanted to know the mass, they would have said what mass. Are you with me?
yeah, so amount is just the quantity.
Yeah, amount is
Okay.
quantity. And
Okay,
think like, what amount of donuts did you eat? You don't answer with 5 pounds. Because that's bad. 5 pounds of donuts is probably like 5 dozen donuts, because you know how light and fluffy donuts are. Light and fluffy and wonderful. Okay, what mass of bismuth are you consuming in the 2 tablets? So here we have 300 milligrams, and we want to know that's of this bismuth subsalicylate. And here, although it's kind of a pain in the butt, we probably want to do this. And we want to multiply by milligrams of bismuth per milligrams of C12H15Bi3O12. Now here, this is C21H15Bi3O12. That's how much 1 mole of this weighs. Here, we have 252.2 grams of bismuth in here. Can we use these 2 numbers down here? And the answer is absolutely. If there's 252 grams of bismuth in 1,086.3 grams of bismuth subsalicylate, that also means that there's 252.2 milligrams of bismuth per 1,086.3 milligrams of subsalicylate.
Tony, is that the 252, the amount of carbon though? Looks like we have bismuth down below.
Right, thank you. Good catch. So 670.27. Now, when they say what mass of bismuth, do we have to answer in grams? Heck no, milligrams is a mass unit. So I'm going to go with this, and I'm going to write 627.0 milligrams of bismuth per 1,086.3 milligrams of bismuth salicylate, because it makes me have to do less work. I don't have to do more work, I do less. So here we're going to do this.
Another question on the units. I don't know if I'm following or missing something, but
Yeah,
looked like we had grams for the whole compound originally.
right here.
Yeah,
Yes, and here I have grams of bismuth.
yeah, and then we went to milligrams. Oh,
Well-
it's just the ratio. Okay, never mind.
Yeah, it's just the ratio, so I could do-
something there.
Yeah, I can do milligrams, nanograms. It's just a
Yep.
ratio.
Yep, got it.
So I'm using my wits, if you will. So 300 times 627 divided by 1,086.3, and we get 1. 0.73 times 10 squared milligrams of bismuth. Now, at first I'm looking at this answer, I'm thinking, whoa, that seems like a lot, but why is it not very much? And the answer is it's in milligrams. So this is 173 milligrams of bismuth when you take 300 milligrams of this stuff. And does that seem about right? And I think the answer is yes, because when you look at 627 compared to 1,000, isn't 627 a little more than half? And if this is a little more than half, then that means a little more than half of 300 should be bismuth, and 173 is a little bit more than half, which is 150. Any questions on that one? Okay, I've got way too many more of these to cover in the time allotted, so this is something that you probably want to take good practice with. Let me just show you a flash on the screen some of what I think are other good problems to do. Now, what you may want to do right now so that you don't have to later is use your snippet, I think it's called on a PC, or use a Shift Command 3 on a Mac to take a screenshot, and you will see the problem here. But these are other problems that I think are really good for you to understand how to do. Let's just take a quick look at this problem. What is the identity of E when this is a compound and E is a non-metallic element? What do we think E is going to be? I'm thinking it's going to be, first of all, something like carbon, nitrogen, oxygen, da, 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 da. You with me? It could also be a metalloid. So that eliminates a whole lot of things when we call it a non-metallic. All right. Here's another one I think is interesting. Consider the mass of a zinc 64 atom. Calculate the density of the nucleus in grams per cubic centimeter, knowing that the radius is this. Now, how would I do something like this? Well, if I want grams per cubic centimeter, you want grams per centimeter cubed, but you're given nanometers. I'd probably take my 4.8 times 10 to the minus 6 nanometers, turn that into meters, and then turn that into centimeters, and then put that into this equation, because I will get my centimeters cubed automatically. Does that make any sense, folks? Kind of like do this as a side problem. What do they call that thing before you eat the main course? An hors d'oeuvre or something like that? So there you go. That's the way I would start this problem. This is based on the same problem. Calculate the density of space occupied by the electrons. And here, they want the density in grams per centimeter cubed, because in the previous problem, they wanted grams per centimeter cubed. So I would take this, turn that into meters, and then turn that into centimeters, so I could use the same formula. And this is the same problem. When you calculate those two densities, what do you find out about the density of where the nucleons are compared to the density of where the electrons are? Here's another good one. A piece of nickel foil is 0.0 or 0.550 millimeters thick and 1.25 centimeters square. It's allowed to react with fluorine to give nickel question mark fluoride. The first question is, how many moles of nickel do you have in your square? So this is something where you might want to do something like this. So here's my square, and this is 0.550 millimeters. What is this length here? 1.25 centimeters. And this is 1.25 centimeters. Now, the reason I draw this out is because when they say 1.25 centimeters square, I'm thinking to myself, we have a square of aluminum. And by drawing it out, it helps me understand that each side is 1.25 centimeters. Maybe I don't need that. Now, this is the density in grams per centimeter cubed. And here we know the volume is going to be the length times the width times the height. But my height is in millimeters. So maybe I want to convert that to centimeters before I use this formula for the volume. Are you with me here? So a side problem here would be convert the millimeters to centimeters. This is a continuation of the problem. I'm not sure what this means. I must have written down the question incompletely. Let me think of this here. Okay, this is if we isolate 1.26 grams of nickel fluoride. So that means you take your nickel, you take your fluorine, and you get this nickel fluorine, and you don't know what the formula is. And you get 1.261 grams of this stuff. And you start off with a mass of nickel. What is its formula? So this is basically a formula from combining masses. And then what is its complete name? Here's another good one for a hydrate. So you may want to snap this guy. So this is the way this kind of looks as a setup. So this is what it means when you dehydrate something. You take all of the formulas of H2O out of the compound and separate them. Now, what happens to the H2O when you heat this? And the answer is it turns into steam, which is a gas, which means it dissipates. So it leaves the material, and what you're left behind with is just the ionic compound. So if you start with a 1.687 gram sample here, and you end up with 0.824 grams of magnesium sulfate, how many grams of H2O were there? And the answer is 1.687 grams minus 0.824 grams. This mass is the difference of these two masses. Does that make sense? So we'll call this the mass of H2O. So what you do then is you take the mass of H2O, turn that into moles of H2O. You take the mass of magnesium sulfate, turn that into moles of magnesium sulfate. And then you take these ratios here. I'll call this A moles of H2O over D moles of magnesium sulfate. And then you get 8 over D mole of H2O over 1 mole. And basically, that's your X. And that's it. All right. Thanks for showing up and thanks for helping me out with that one problem where I messed up with the hydrogen. All right. Turn your mics on and say goodbye to everybody.
Bye, everyone.
Thank you, bye.
All right. I'll be posting this as soon as I can get it ready. Toodles.